What is going on, everybody, and welcome to a video on autoencoders. So autoencoders are neural networks that are trained to encode and subsequently decode input information. So by encoding, what we mean is generally compressing it or denoising it or just reducing it to fewer information than the input. Ideally, it doesn't have to be that way. So another form of encoding might just be we want to change the format of the data. But generally it's going to include some sort of shrinking of the size. You would not use an autoencoder, at least I haven't seen any, for actually the purpose of like video compression, let's say. You would probably want to use some sort of mathematical proven formula for this. But instead, autoencoders are very popularly used with more of your advanced and complex problems with machine learning and deep learning. I think the best way to understand stuff like this is just to do it. So let's go ahead and jump in and learn a little bit about autoencoders. So the first order of business is that we get ourselves some data. So we're going to import Tensorflow as TF. We're going to, from Tensorflow, we're going to import Keras. We're going to import, I think matplotlib.pyplot as PLT. We could also use CV2 for visualization. There will be text-based version, or there is a text-based version of this tutorial. I will put a link in the description. In that, I'm going to use OpenCV instead because you can very quickly like cycle through things, but I always have problems on various, it's like the way that you handle it is different on each operating system. I know Matplotlib will act the same way that I'm used to, so I'm going to use Matplotlib here. We're also going to, I think I'll still use CV2 probably in this tutorial to resize things, so I will still import it. And then we'll import NumPy as NP. So to begin, we are going to specify the X-train, Y-train, X-train, Y-train, and then X-test, Y-test, even though we don't actually need that information. And we're going to use the MNIST dataset. The reason why we're going to use it is, honestly, the dataset doesn't really matter that much. If you have your own, we're going to be working with images, so if you've got your own images, and especially if you just want to like grayscale those images real quick, feel free to pause it and use something else. You don't have to use this data set, but that's what we're going to use for this tutorial. So tf.keras.datasets.mnist.load. So what we have here, if you're not familiar, we can just show plt.show, and we'll show xtrain 0. And actually, a couple of things. First of all, we'll say cmap gray, and it's not show, it's imshow if we want to show an image. So once we get the import, load, is it like load? Oh, it's load underscore data. So load data like so. Okay. Cool. So here we have like a 5, for example. We could check another data point, a 0, and so on. So they're just handwritten digits and some more further information. Xtrain, say 0.shape. They're 28 by 28, and as you can see, they're grayscale. And also, if it was like RGB, it would be 28 by 28 by 3, for example. So in this case, it's 28 by 28 data, and if we just run the numbers real quick, we see that 28 by 28 is 784. So when you feed this through a neural network, that is 784 unique features. If it was RGB, it would be multiplied by 3, and now you would have actually 2,352 features. This isn't RGB, but in the future, and hopefully at the end, I'll show an example of RGB, because certain things change with the autoencoder, but we'll get there. So anyway, in this case, it's 28 by 28, 784 features, which is a lot of features. So luckily, the MNIST dataset is actually a really easy one for neural networks to learn, and we can talk a little bit about why that might be. But it's a very easy one. But for neural networks, 784 input features can often be very challenging. So the idea of compressing those features down in such a way that it would make learning for the neural network easier, that's always good. And then if you've got features that are noisy, i.e. kind of useless features, why not toss those out? So this is us using a neural network to hopefully figure out these things. So in a lot of cases, for example, maybe the features are all useful, but certain features have relationships with each other such that maybe you've got 5 features, but you could actually, because of the way that they interact with each other, 5 features could actually be condensed into 2 or 3 features. And then imagine that spread across hundreds of features. If you're able to do something like that, you can simplify the problem. And with neural networks, if you're having a hard time getting a neural network to learn something, the first thing you should always be thinking of is how can we make this an easier problem for the neural network to learn. And when a neural network is training, it's trying to do kind of 2 things at one time, right? It's trying to figure out what is this data, what are the relationships between these features, and it's trying to do, say, classification. So it's kind of doing 2 things at once. And the idea of an autoencoder, as you'll soon see, the input is the output. So it's actually just mapping the input to the output, and the idea is to have some sort of bottleneck along the way. And doing that hopefully makes it easier for the network to learn. So we know we have 784 features. Now with all image data, like right now, let's just print out xtrain 0. We can see the values are everything from 0 to, there's probably, I don't see a 255, I see a bunch of 253s, but I assure you it goes to 255. Anyway, the data is 0 to 255, so generally one of the things that we do with image data is just divide by 255, including if it's RGB. So we're going to say xtrain equals xtrain divided by 255. You could also say something like xtest div equals 255. I think either of those should work, so we'll do that. Can we not get away with doing that? Div equals. I thought we could do div equals. I guess not. I'm not sure why that wouldn't work. Xtest div 255. Okay. Anyway, I'm sure maybe that was really obvious. I don't know. Anyway, so now we have our data, and so just to show it real quick, it's kind of ugly, but I assure you all of these values are now between 0 and 1 instead of 0 to 255. And again, for neural networks, we generally like to keep data between -1 and +1 or 0 and 1. So in this case, it's between 0 and 1. So, okay, so we have our data. We've pre-processed our data how we'd like, but the problem, again, is it's 784 features. So what we're going to try to do is condense those down. So we're going to start by defining basically an autoencoder is going to consist of 2 models into 1 model. So we're going to have an encoder and we're going to have a decoder. So we're going to say encoder underscore input, and this is going to be a Keras.input layer, and the shape is going to be, oops, it's actually shape. It will be a 28 by 28, 28 by 28, and then 1. And again, if this 1 this is how many channels is it. So if it was RGB, you would put a 3 there instead, and then we'll give it a name, and we'll just say image for now. So that's the input to our neural network. Now what we want to do is attempt to condense it. So in our case, with the MNIST dataset, it is grayscale, so we don't have these 3 channels to work with. It's pretty simple data. We don't have to use any convolutional layers. Now, this will allow us to simplify and for me to show you like how this works. Also, a lot of problems that use autoencoders aren't doing it on image data at all. Like you don't have to do this on image data. The only reason we're doing it on image data is to because you can actually visualize what the autoencoder does, which I think is really cool. So we're not going to use any convolutional layers, and then if you do use convolutional layers, it adds a slight degree of complexity. But again, at the end of this tutorial, I will show you some code that does use convolutional layers, including pooling and all this kind of stuff, because that makes it a little more challenging. But for now, we'll keep it nice and simple, and we're just going to use dense layers. And to begin, we are going to flatten that. So keras.layers.flatten. And we're going to do that to the encoder input layer. So I think I want to say this is like Keras functional as opposed to using the sequential type of model. You can do like the model.add if you want and just add a flattened layer and so on. I haven't really decided which one I like. I've started kind of using this one instead. I almost think this makes more sense. I don't know. Anyway, just take note because I think this might be the first time I've used this on the channel. So we have a flattened layer. So again, that's going to flatten all of the input to be basically 784. So then we can have just a dense layer. So we'll just say x equals keras.layers.dense, and we'll go with 64, and this will get multiplied by this x here. So we have that dense layer. We need to do activation equals rectified linear. And honestly, that's probably all we need for our encoder. So I think what we'll do is, we'll just call this, rather than x, we'll say encoder underscore out, and that will be equal to keras.layers.dense. And that's probably all we need. More complex information might require a more complicated encoder, but often it's the case that you don't need more than this. And again, because the problem that we're trying to solve here is actually the easier of the many problems that neural networks have to solve. And again, the benefit of using an autoencoder is it's kind of it's that sort of separation of tasks, right? The autoencoder's only task is to solve this sort of condensation problem. So that's our encoder. And in case we want to use the encoder later, you could do this for both. We're actually only going to show the encoder layer later, but for now, we'll just say encoder, and that's going to be equal to a keras.model. And that's going to be everything from the encoder input to the encoder, and I kind of want this to be output. And we'll give it the name we'll call encoder. So now we have our encoder. Now we need our decoder. So again, the autoencoder is going to take input and map it literally to the exact same input. So the only constraint that we have with an autoencoder is that the output layer is an exact match to the input. So in this case, it needs to match 28 by 28 by 1. So the way that we're going to do that is, first of all, we could probably just go straight to the output, but we'll go ahead and we'll have a dense layer first. So there's a couple of ways we could do this, but I think probably we're just going to throw in a dense layer. So here's what we'll do. We'll say x equals keras.layers.dense, and we'll say 784. We know that we need to end on 784 values at some point, so we'll just throw in 784. A 784 dense layer shouldn't be too complicated for us to use anyways. So activation equals rectified linear, and this gets multiplied by your encoder. And then finally, so we have 784. We know 784 is the result of 28 by 28. How do we get this back to be 28 by 28? We need that to go back. Alternatively, there's a million ways you could do this. You could, and it might be quicker using maybe NumPy even first. I haven't actually tested this, but you could also just, prior to feeding it through the neural network, we could have actually flattened our data, and then it would already be 784, and you could actually end on 784 probably. But we'll keep it this way, especially because eventually, if you use RGB data with 3 channels, then it becomes way more taxing, I think, to flatten it prior. Anyway, so we'll do it this way, dense. And the big takeaway, I hope, is that there's a million ways that you can make an autoencoder. Literally, the only thing that matters is that you map input to input. That's it. So Keras layers dense 784, and then we'll have our and actually, let me think about this. This really should be let's see. So dense. I think probably. So we've defined our encoder, and this could be our decoder. let's see, decoder input could just be this like dense layer. You could start with a 64. I don't actually think, a lot of times you're going to see the decoder is almost an exact mirror representation of the encoder. It's probably not necessary in this case, so I'm actually just going to leave it like that, and then we'll say, if it doesn't work, I'll fix it, but we're going to say decoder underscore output. All we have to do here is keras.layers.reshape, and again, what is the shape that we need this to be? It's the exact shape from that input, right? So 28, 28, 1. And then that is multiplied by decoder input. And that is our decoder, right? All we needed it to do was to just decode out to 784, basically, and then reshape it to 28 by 28. And now it is an exact match of the input. So now all we need to do is we're going to specify an optimizer. That's going to be tf.keras. And in fact, I don't even think we need to say tf.keras because we're using Keras already. So we'll just say keras.optimizers.atom. We're going to specify our learning rate of 001. For this problem, we don't actually really need a decay, but we'll just throw one in there anyways. Okay, we've got our optimizer. Now we're going to specify our autoencoder model. And again, this is like our encoder model. It's just going to contain everything from, and in fact, I'll take this, copy, paste, everything from encoder input to decoder output. And we'll just call this autoencoder. And then finally, let's do autoencoder.summary, and let's make sure that we haven't made any mistakes. I need to delete this so I don't have to see this anymore. Let's just do that. Train. Activation. Oh, encoder. It needs to be encoder output, not the encoder model. Okay, that was quick. Okay, so as we can see, it does indeed end on the exact same. Obviously, like for example, our reshape would fail if we used anything other than 784 here. So again, what is a dense layer, right? A dense layer is going to produce literally just a vector of 700, in this case, 784 values. And then all we're doing is we're just going to have that, whatever the output of those 784 neurons is, we reshape it to a 28 by 28 by 1, and then boom, we start optimizing, calculating loss, all that fun stuff. So, okay, so I think we're actually good to start training. So let's see, I'm trying to decide. I kind of already know how many epochs is required. I kind of, in the text-based version of the tutorial, I did like a little loop, only because I didn't actually know how many it would take. But in this case, I think we can just do autoencoder.fit. And in this case, it is xtrain, xtrain. So again, this is your x, this is your y. In the case of an autoencoder, you're literally mapping x to x. You're mapping features to features. And the whole point of all of this is to hopefully go from 784 features down to 64 features. And then we can prove that it worked by then decoding it from these 64 features. Again, that's 64 features. That's just a vector of 64 values. We're decompressed basically to 784, and then we reshape it. If this does work, what does this tell us, right? It tells us that rather than feeding through, like we have this autoencoder, so we've trained this encoder to take an image of 784 values and condense it down to 64 values, yet still contain the same meaning. And then what we could do is we could, before we pass data through a different neural network, if our training data are these MNIST images, rather than feeding through the 784 samples, we could actually feed through the encoded 64 samples, thus making the problem easier on the model to learn. Also, we can change data types and more on that later. But first, let's make sure this works. So we fit x to x, x train, x train. Let's see if there's anything else. Epochs equals 3, and then batch size, probably 32 will be good enough. And then validation split equals 0.1. Okay, let's see if that works. No. Oh, we didn't compile the model. Dummy. Let's go ahead and let's get that done, huh? So we'll do Autoencoder dot compile. Where did we define the optimizer? I got so busy with the summary. We did get the optimizer in there. So compile, and then we'll just say opt and loss equals, we'll go with mean squared error. Let's try that one more time. Okay, the model is training. And now what we want to do, while we let that go for one more epoch, is basically we're going to now take our X test data. So we trained this model on the training data, so it was basically X train to X train samples. Now we're going to start referencing the X test, and the first order of business will be to come down here. Looks like everything is done. We have the autoencoder that's trained, but that also means we have our encoder trained up here. So I can come down here, and what we can say is we can basically just say example equals encoder dot predict. And again, predictions, I say again because I've had to say this like every tutorial, predict takes a list of predictions even if you only have one prediction, and it outputs a list of predictions even if it was only one. So I'm going to end with 0, and in the list we're going to go with X test, we'll go with 0. And we can print example. Oh, we didn't, let's see, I think we have to, yeah, we got to reshape it. Moments of truth, and then just ruined. Reshape, and what is it? -1, 28, 28, 1. So again, it's taking a list, and in this case, it only has one value, so we're just going to reshape it essentially to be this unknown size, which happens to be 1, by 28, by 28, by 1. Try again. Cool. So now we have, this is the encoded version, and as you can see here, if we do example.shape, it's 64 values. So we went from 784 down to 64, which is 784, about 8% of the original size. We can also visualize this to some extent if we did something like plt.imshow. Now again, this is not meant to be an image, so take this with a grain of salt, but example dot can't type today. Since it's 64, we can reshape it to an 8 by 8. I want more space. I don't like staring down. There we go. Imshow, example, and then CMap. Wow, I can't type today. I don't know. Great. Okay, so this is our condensed version, and as you can see, we actually have kind of a lot of what I would suggest are actually still useless pixels, but it's kind of interesting. Okay, let's see what the actual encoder said. So, and also, let's go ahead and plt.imshow the, let's see, test. What did we do, 0? And actually, it's xtest, I think, xtest 0. And then again, CMap equals gray. I'm actually kind of worried that, I'm not sure this will translate. We're going to find out. So the way that we find out is by actually doing an autoencoder. So we'll do this time, we'll say AE out equals autoencoder dot fit, and actually we'll do really the exact same thing that we did up here, or not dot fit, dot predict. So we'll scroll down, dot predict. So we have the prediction, and then what we would do is, we don't want to actually run the reshape, so we'll just do plt.imshow the AE out. AE out, boom. And no, that did not work. Fascinating. I almost wonder if we do need that that extra layer. I'm actually kind of interested if that is truly what is necessary. I really did not think that we were going to need that input. Let's see. So we went straight from 784 to the reshape, and the way I initially did this was essentially had one more. So the input was actually 64, and then it went to 784. We'll say X here, X here, and then this would be decoder input here. Let me make sure that's exactly what I had. Otherwise, that should be the same. I'm going to be super. Let's see what happens. I really didn't think that extra 64 unit layer would do anything. So now I'm concerned there might be some other issue, but yeah, dang, there's something else going on here. What is it? Let's see. Flatten, dense, rectified linear. Almost going to have to, I think, maybe I'll copy the original and just see if we get the exact same. What else could this be? Xtrain. Unless, did we possibly run, let's do this. Part of me wonders, because we might have run that div by 255 twice. That could be part of the problem. I don't work in notebooks often enough that I think I might have run the div by 255 2 times, and that might have caused it, but I'm not sure. Yeah. I think that's what it was. That's interesting. So, in case you didn't follow, my guess is what caused the problem was when I did this div equals here in this cell. What did we do it on? So basically what we did was for the training data, we dived by 255, and then this errored out, and then I dived by 255 again. I'm gonna wager that's exactly what happened. I'm not sure. I kind of want to. Oh, I really want to find out if that's what it was. So, because that would make sense. So if we just ran this one more time and then we do all this again. Sorry to waste everybody's time, but I'm actually super curious. So if this doesn't work, especially if it shows all those like dead pixels, that would also explain why so many of those pixels were like kind of dead. Yeah, interesting. Okay, so let me go ahead and unscrew this up. Where was the div? That's what I get for like I never work in notebooks. It just makes sense for me to be working in a notebook for like this tutorial, and that bit me in the butt. Did I get it? Cool. Okay, so what I'm going to do is I'm just going to restart kernel and run all cells. Hopefully we don't run into that again. Oh, but actually, so now I want to go back because I kind of want this one. Okay, so actually I want to say decoder input, and then it goes, let's see. So I want that to be commented out. I want this to be back to decoder input, and I want this to be 784. Still working. Restart kernel and run all cells. Okay, because I want to see if this actually works. Like it should work. To just go straight to 784 one dense layer, that's more than enough to learn this data, and then we can get back to the tutorial now. So you've already seen that it actually does work. It looks like that worked. Cool. So yeah, so this was the original input data, and then this is the output. I mean, and we can test. We could do a couple other ones. So let's say we want to go with 1. Okay, it's a 2. We'll throw in a 1 here again, and it's a 2. And in fact, we can come up here. Example. We need to streamline this for sure. But we'll do this. So this is our condensed 2. And yeah, so you can see that this definitely worked. And I think we'll make our change first, and then I'll change some of this code. But what's important to recognize again is we went from 784 features down to, I don't know, this many features, 64. And then we decoded, so we encoded down to 64 features and then back up to 784 to essentially reproduce the number that was the input. It's a little dimmer. It's not a perfect replication, and that's why it's not like this would be a great method for, again, doing like video compression on a website. YouTube is probably not using autoencoders. Again, the point is for features, condensing features down, and it's doing so in an unsupervised machine learning way, in that, as you can kind of already see here, this 2 and this 2 are slightly different. They're not exactly the same. So I think to make this even more clear, we can take this down quite a bit. So we've got 64 here. Could we condense that down to 32? So I will go ahead and do that. And in fact, I am going to condense this code. Actually, I want to cut that, paste that. So we will run that. I'm going to get rid of that. We have our example information. I don't know that we need to have the shape, but we'll go ahead and print example.shape as well. This one, what do we go with? Do we say 32 this time? Yeah, so we're bottlenecking to 32 samples only. So again, 32 print, let's say 32 out of 784. So this is basically condensed down to 4%. We can print example rather than reshaping to 8 by 8, 32. Yikes. We don't really have a great, I guess 8 by 4, right? Yeah, that's, I guess, a way. Like, again, these image representations are just so we can see the values. That it does not actually meant to be an image, because actually this right here at the output from our example is the output from our encoder. And what is that? It's actually just a dense layer output. It's just a vector of values, period. So we just happen to reshape it and make a pretty image out of it, but that's it. So, okay, so we get rid of this. We can keep that. I'm going to get rid of this. And the original, cut, paste. So this was a 2. Are we again using test.1? Yes. Variables would help a ton. And then we will paste this here. So that's AE out. And then we'll go ahead and do the mshow right away. So now, let me just do this real quick. And I think we'll just delete these. Okay, so again, it worked. We have a couple of like dead pixels here, but for the most part, it looks like everything is working, pretty well. So again, we can go with xtest3, for example. We can change this. Let me go ahead and actually run this one, run this one, run that one. Okay, hopefully it's going to be a 0. xtest3. And there we go. So we have a 0 again. And again, it has a lot of the original features, like there's like a little extra bit up here on the 0. It has that too. And it's still missing some value here. It is slightly dimmer, but it's very clearly a 0. And, we can keep going and just see like how tiny can we get this. So let's do a 9. So like a 3 by 3 essentially. So we will retrain that. And let's just rerun essentially everything here. We don't necessarily, unless we see anything like super interesting, I won't reiterate through a bunch of different samples, but you should get the idea here. Whoops. This should be a 3 by 3. So, okay, so this information, does it contain a 0? And it does. It's not the best 0. It's not the most beautiful 0 that we've ever seen, but it is a 0. And to me, I think this is super cool that we condensed 784 values into a vector of 9 values and it did a pretty good job. It's still very clearly a 0. Let's go back to, what was the 5? Was it 0, I think? Oh, no, I guess that was a 7. So let's show that one real quick. Let's make sure. Okay, so these are clearly both 7s, but this is not the same 7. So what's happened here is we definitely have a neural network that has just learned, okay, this data is a 7, so encode 7, but it's not the exact same 7. Because again, we've come down to literally only 9 values, which, I'm sorry, I just find that fascinating. I know MNIST is easy, but if anything, this should show you how easy of a problem MNIST is to solve, because we literally condensed down to 9 values, and we're able to produce this. That's insane. That's just insane. So, okay. So that is autoencoders. We can show, I think I'll show one more interesting aspect of the autoencoder. But again, so like, imagine you're the autoencoder. How might you condense this information? Well, really quickly with the MNIST data set, one thing you could do is chop away all corners, right? Like this corner here, this corner here, this corner here, and this corner here. They're almost always dead information, right? There's no information there, right? So immediately you could probably chop this data down fairly considerably, but I don't know about you, but there is no way I could condense it down to be 9 values. I just think that's crazy. It's just crazy. Again, we can visualize those values. Print example. These are the values, right? That's cool. I just think that's super cool. Okay, so all right, so we've made it this far. The next thing I want to show, I don't think there's really any benefit in me coding this. I want to show you more example of noise reduction. So I'm trying to find it. I put it in the text-based version of the tutorial. It's a very poorly written function. Where are you? Here we go. So I'm going to make a function here called add noise. And what I'm going to do first is I'm going to re-expand this out. Probably condensing to 9 values is a little silly. But so we're going to pull back to 64 here. And I'll go ahead and just retrain that model. I'll leave this information here just because it's interesting. We'll come down here and we're going to add a function, and it's just literally, it's a function that's just going to iterate through every single pixel. And in fact, I'm using random choice. So let me go ahead and import random as well. And then randomly, this is a 5 out of 100% chance it will randomly change that pixel value essentially. So import random, and so it's just going to add noise to an image. So what we can do is we can say, okay, there's our function. We will say noisy equals, and we'll say x test 0. Oh, whoops. Needs to be add noise x test 0. Add noise. And then now we can, let's just go ahead and plt.m show, we'll show our noisy image, cmap equals gray. So now we have a noisy 7, okay? And what happens with, let's see if I can hopefully copy and paste a quick AE out here. Boop, come down here, paste, and rather than x test 0, it will be noisy. Okay, and then we will do a plt.m show, not noisy, AE out, cmap equals gray. So what you see is a pretty significantly noise reduced variant, right? This is the noisy 7, and then this is the kind of the 7 that came out of our autoencoder. So what didn't we do? We did not train an autoencoder to take noisy examples of photos, and then so like, you could train a model where you have your clean data set and then you have your input be this add noise, a bunch of add noise examples, and then you could train a model to remove noise. But that's not actually what we did, right? We trained an autoencoder to just take images and like encode them into the meaning of that image. And in our case, the autoencoder, again, because it's unsupervised machine learning, has just kind of figured out like this group of images goes together, and here's the generic version of that group, right? And we can even see that here, like this seven doesn't quite match the original 7. But it did a pretty good job removing that noise, because the autoencoder has just simply learned that the meaning of the value, or the meaning of this input data, is actually somehow in this number. Again, it's unsupervised. We don't know exactly how it has done this. But I think, hopefully up to this point, you have seen just how much autoencoders can compress data, right? We took 784 features and compressed it down to 9, which, what is that, 9 out of 784. Basically 1%, which is absolutely nuts. I'm sure that quite a few numbers condense down to this, to that, 3x3 or 9 values. I'm sure a few of them don't work, or probably even quite a few. I wouldn't be surprised if like 20% of the data set's illegible. But you wouldn't condense it to 1%. But the idea is to just show you that you can use autoencoders to compress data down. Now, the last thing I wanted to show with autoencoders is not only can you do noise reduction and compression, the other thing you can do is just change the overall, let's see, this is for something else. Pay no attention to my notes. You can change the format of the data. So in this case, I don't think I'm going to run it. I don't really see any benefit to running it. Maybe I'll put it in the text-based version of the tutorial if you want to play with it. But essentially what it's doing is it's taking photos of cats and dogs, and they're color photos. I'm reshaping all photos to be 64 by 64. We are doing the div by 255, but we're keeping the 3 channels, right? So the RGB channels. And then we're running it through convolutional filters, right? And then we're also doing max pooling. In fact, I kind of want to run it. I think let's see. Maybe I'll run it. Okay. So let me just, Python 3. I think I'm running, yeah. The way I define Python is different on like Windows, this Linux machine, and that Linux machine. So it's super, I always forget like which one, how do I call Python? And like which version of Python I want. Anyway, we're running it for 15 epochs. I don't think I'm going to like finish this training for you guys, but I'll let it at least start, because really what I wanted to show is right here. So I wanted to show the this model summary. So this is what I was talking about before, where, let's see, how do I make it? There we go. Where essentially, like what we're doing here is we are taking in 64 by 64 by 3, which if we did the math on that, I think it's like 12,000 or something. 64 times 3. Yeah, 12,288. So if you were to just flatten out a 64 by 64 RGB image, it would be 12,288. Now, why would you ever want to flatten it out? Well, for example, I was tinkering with with trying to feed a sequence of images through a transformer model. Well, a transformer model expects to take encoded input, right? A vector of values, not a 3-channel image. So I was just curious, can we condense this down to a small enough value that you could then pass a sequence of images through a specific transformer model? And so I was just kind of playing with that. And essentially what's going on here is you have, maybe by the time I get done yakking, we'll actually see some examples and before some sort of stupid error. But anyway, you have your input, which comes in as a 64 by 64 by 3. We do some convolutions to it, but each time you do a convolution, pay attention, because like in this example, you're saying 64, and then the window is 3 by 3, and then you can see what it winds up generating in terms of values. So each of these are vectors that, if at any point you were to flatten, would be quite large, right? In this case, it's 64 by 64 by 3. If you flattened here, it's 64 by 64 by 64. It'd be gigantic. But then we do the pooling, and now we've pooled down, because the pooling layer, I think, was a 2 by 2. Yeah, a 2 by 2. Now we're down to 32 by 32, 64, still giant. But then we do another convolution. Then we're doing one more flatten. or did we do 3 pooling? I can't even, I think this is only showing 2, I think. No, my eyes are deceiving me. We're doing 3. Anyway, we pool down to essentially flatten to 8,192. But we're not done yet, right? Then I'm just throwing in a dense layer of 512 just to do it, right? And that's the end of the encoder. So we can come over here and see the flatten, and then the encoder output is 512. So this is officially the bottleneck. So the question was, could we condense down to 512 values, a vector of 512 rather than a vector of 12,288, right? And we're getting the benefit of using convolutional layers. And again, you could always simplify this, right? You may not need to use RGB images. You might grayscale the images first. That divides your data by 3 right out of the gate. So anyway, take note. But anyways, you essentially, as you convolutional filters down, and then you're also doing your pooling, you do the exact opposite on the way back, right? You've got your convolutionals, but then you have upsampling. So then you upsampled, but to the same degree that you pooled. The only thing you have to be careful about here is that there's no padding going on in your pooling. So if there was, there's probably ways that you could kind of get around it, but it becomes very challenging to get it to upsample all the way back to the exact same input shape that you started with. So generally, you're going to try to work with a very specific input shape that you can both pool down and then upsample right back up. And again, literally, you're using a layer that is an upsampling layer. Anyway, did we never? Maybe I threw an error. I guess we threw an error. I wonder what the problem is. Internal error. Failed to get convolutional algorithm. Why would that happen? Let's just run NVIDIA SMI. I'm actually not really sure. So we've got the 2 GPUs. Isn't this one running on GPU 1? Yes. So why? I'm not sure why that errored. You don't have to see the output of it. It's literally just an image of a cat. But it would be fun to show it to you. But yeah, this one is full, but it's because we're running here. I'm actually not sure. Why wouldn't that... I'm not sure why I hit that error. Anyway, I'm not going to waste y'all's time and show it to you. Like I said, it's literally just a RGB picture of a cat. But I can post the code, and I'll put it in the text-based version of the tutorial if you want to tinker with it. It's a cats versus dog data set from Microsoft. Anyway, quite a long tutorial. But there's just so much that you can tinker with here that we've really barely scratched the surface, because we didn't even really talk, like we showed the encoder side of things. We didn't really show too much decoder-wise. And really, you might be actually, like in many cases, you're focused actually primarily on the encoder, but there's going to be plenty of times where you'd be focused on the decoder as well. But the idea is always pretty much the same. It's to get a model to focus very specifically on a challenge that you have, and give it only one job to do rather than the many jobs that a neural network has to do generically at the beginning of training, given a data set. Also, I just think it's freaking awesome that we can take, I know it's the MNIST data set, but condensing it down to only 9 values and still producing the input data. I think that's cool. I think that's really cool. So anyway, I think I'm going to stop it here. I think we're at like 50 minutes. That's quite a long tutorial. So anyways, if you have questions, comments, concerns, whatever, feel free to leave them below. Also, if you like getting into the more nitty-gritty with neural networks and tinkering, I suggest you check out the Neural Networks from Scratch book. I don't know if you've ever heard of it. But yeah, it's the book by Daniel and myself. You can check that out at nnfs.io. Otherwise, I will see you guys in another video.